In the video, I've got another exam walkthrough for you from Oscillations, and I've got another paper here for you. It says a Bluetooth speaker enables music to be played from a phone or other mobile devices without the need for wire connections. The speaker rests on 3 rubber feet as shown, and so we have been given this rubber. Rubber is a material that can oscillate back and forth, so we have given this rubber material, and it says the rubber feet maintain contact between the speaker and the surface it is on. Now, these rubber feet will be in contact with the surface, which will be a hard wooden surface. So it says, why is there a loud sound when the speaker is on a hard wooden surface? So what's going to happen here is we have the speaker, and the speaker is playing some music. So the speaker, when it plays music, it's going to exert a force on the air upward, and then it's going to come back, and then back and forth it will move up and down and exert a force on the air up, and then and then it's going to come back down. And so that's what's going to be happening to the speaker. I'm sure you guys have seen it, right? The speaker, when it plays music, it's going to move up and down. Now what's going to happen is, as the speaker is moving up and down, when the speaker is being moved downwards, it's going to exert a force on this wooden surface. So the wooden surface is going to experience a force. And then what's going to happen is that now a good way to imagine it is, imagine you're holding the speaker on your hand and you play really loud music. You're going to experience a force on your hand. That's the force I'm talking about. And what's going to happen is, this wooden surface, when it experiences this force, this wooden surface will start to oscillate. So the force from the speaker forces the wooden surface to oscillate, and as the wooden surface is oscillating, it's gonna cause the air to oscillate back and forth as well, and that's gonna cause that loud sound that will transmit through the air. So here's the answer. The force exerted on the wooden surface by the speaker causes it to oscillate, so it causes the wooden surface to oscillate, and then the wooden surface drives the air into oscillation, and thereby producing a loud sound. So that's the answer, and that will give you 1 point, and the second point will come from here. In the next part, we can see for certain frequencies of sound, there is much larger increase in the loudness of the sound produced. Explain why this increase in sound occurs for certain frequencies. Now, these certain frequencies are the whole number integer frequencies, driving frequencies of the natural frequencies. Now, at these frequencies, this is a pretty common question. It's talking about resonance now. So you have the speaker, this is the rubber material, this is the wooden surface, and this is the air. So as the driving frequency of the wooden surface is equals to the natural frequency of the wooden surface. So you can write it in terms of the wooden surface, that the driving frequency of the wooden surface is equal to the natural frequency of the wooden surface, or you can talk about the air, that the frequency at which the air is being driven at is equal to the natural frequency. And because of this, what's going to happen is the maximum, or I like to write it like this, the greatest possible energy is transferred to the wood. The wood oscillates with maximum amplitude. This causes the air to have increase in loudness of sound. Okay, that's a good answer right there. Remember, the key terms here is, you don't only write the driving frequency is equals to natural frequency. You talk about what's driving frequency, what's the natural frequency. Talk in context. Then write this: greatest possible energy is transferred. They like seeing stuff like this. Don't write increase and decrease. They don't want that. because if you know the graph, you know that the frequency at which the amplitude is maximum, they want to hear those words. They want to hear the maximum amplitude. They're going to give you points for those. So 1 point for this, 1 point for this, and 1 point for this. You're going to get 3 from here if you write like this. And always write in context. Okay, so that's that. So I'm not going to read these, but I just want you to go through these yourself by pausing the video and by understanding what's going on. So just go through it. This is a response which got both the marks. You can see what the examiner wants from an ideal answer. And this is from the other response. I want you to just see here what the student has done and why he's gotten all the marks. He has mentioned when the wooden surface is forced to oscillate on or near its natural frequency. So he has applied the definition to a context of the wooden surface. He has written maximum energy transfer. That's a key word, maximum energy transfer. And then he has written that hence the amplitude of oscillation is large. So he's gotten 3 marks right there for that 3 points right there. And then he's written this results in a large sound output. So you have to always write those keywords that are there in the mark scheme and understand why those words are the way they are, okay? So that's that, and I'm going to also show you the mark scheme. So there's the mark scheme. Okay, next question. A set of scales used to weigh vegetables in a shop is shown. When vegetables are added to the pan, the weight of the vegetable causes a spring to extend, and then it causes the spring to oscillate, and the pointer moves as well. And they've given you a graph of elastic strain energy and extension, and they've given you it up until 0.1 meters. And they've told you, show that the force constant of the spring is about 100 Newton per meter. So what you're going to do here is you're going to take 2 values. So I'm going to take 2 values from this graph. And those 2 values will be, so we're going to take this value right here. This value right here. That's going to be, so what we're going to get is the elastic strain energy is going to be equals to the 0.6 joules, and then the extension is going to be equals to 0.1 meters. So we'll plug it into the formula. E is equals to half k change in x square. So 2 times 0.6 divided by 0.1 square, and we're going to get 119 Newton per meter, which is approximately 100 Newton per meter. So that's the answer to the first part. So next it says when a potato is placed in the pan, and when you place the potato, it's like adding a weight to a spring mass system, and that's going to cause the entire thing to oscillate. So imagine this. So you're adding a potato here, and it's going to cause the entire thing to oscillate up and down. So that's the oscillation we're going to be talking about. And basically, they have been given the mass, and they just want you to find the frequency. So you put the potato, and then you put it down, and it's going to oscillate back and forth. So they want you to find the frequency of that, and we know that frequency of this type of system is 1 over 2 pi square root k over m. It's going to be 1 over 2 pi square root 119 over 0.45. So that's giving me an answer of 2.58 hertz. I'll also find the time period because I'll later need that as well. That's going to be 1 over f. So let me just find the time period as well. 0.38 seconds. Alright. So then it says this is an example of a damped oscillator. Explain what would be observed when a potato is dropped onto the pan. So when you drop the potato onto the pan, right, this is the pan, this is the spring, and this is the pointer. When you drop the potato on here, the spring will oscillate, but in a damped system, the oscillations amplitude will decrease. The main point that examiner, so you're going to 1 point there, the main point that examiner wants is that energy is removed from the system by the resistive forces to the surrounding. Basically, examiners want to understand that that in damping, energy is lost and it doesn't come back. And that's going to give you the second point. It's a common question, but many students, they don't understand what the examiner is looking for. The examiner wants you to understand. He looks for students who understand that energy is removed and it doesn't come back. If you want, you could also write that energy doesn't come back. Energy doesn't come back. Right? That's how important this point is. So of course write it like this, but you have to really express that point. Okay, so that's important to understand. Now, next thing, sketch a graph to show how the displacement of a pan from its final equilibrium position varies with time. Again, this is a damped oscillation, and it's a light. This is having a light damping. We're not in a heavy damping or critical damping. Okay, so what we're going to do here is I'm going to draw a couple of. You have to make sure that in light damping the time period is constant. So I'm going to draw a couple of lines. So you can do this with your scale. A couple of lines right here. I'm going to be a bit more precise and put 0.38 here, and then 0.77 here, and then 1.14. Okay. Actually, I think the space would be too less. One sec. Let me just move around. So here I've improved this a little bit more. Now you're going to draw a couple of cycles. You're going to draw one cycle like this. Make sure the amplitude is same. Then you're going to have the second cycle with a lower amplitude. And then the third cycle with an even lower, it's a bit bad, with an even lower amplitude. You're going to get the first point for having the constant time period and the second point for drawing more than two or more cycles with a decreasing amplitude. Okay, so where's the mark scheme for this? You can just go through it and see it for yourself and let me know if there's any doubts.